Okay, let's continue. So this example shows the difference between the environment variables and shell variables. We in a shell, right? So this is a bash shell, and we run the string proc $$ environment. So this will display all environment variables of the current shell, of this shell. And we don't, because it's very long, so we don't want to see everything. We just filter out whatever environment variable has a string log name. So we grab log name, that means we filter out only things that has a string log name. So we see that the log name is seed, which is the current user here. Okay. And now on this shell, we try to echo variable log name, and we see is also seed. Then we try to assign this variable another value. So we assign log names as Bob here, and we try to see what's the content of log name variable. It's already changed to Bob. Okay, so it is Bob, but when we run string proc display all the environment variables of the current process, do we see log name is Bob? No. When we run this command again, we still see that log name is seed. Okay, it's strange, right? So we have two different variables. One log name is Bob and the other log name is seed. So that's why these two concepts are different. We try to unset log name, that means we try to remove this variable, and we try to see what is its content after removing this variable, and we have nothing. Yes, good. So now there's no more variable named log name, but we run string proc $$ here environment, and we grab filter out only log name. Okay, and we still see log name is seed. Oh, so even no more variable log name, but we still have log name is seed. So what was the difference? The difference is that when we run this command, we see the environment variables of the current process. Okay, so its log name is seed. So this is an environment variable. But this log name is not an environment variable, it's just a shell variable. So this value seed is the same as the environment variable, but it is a shell variable. And when we change this variable to Bob, actually we don't change the environment variable, we only change the shell variable. So that's why when we change it to Bob, this is only the change of the shell variable. It doesn't change the environment variable. It's still Bob here, right? It's still Bob for the shell variable. And now we display the environment variable. We still see that it's still the same. It's still seed. So this is a shell variable, and this is an environment variable. They are different. Now we see the difference. When we unset log name, so that means we only remove the shell variable. We still have, we see the shell variable now is gone. It disappears. But the environment variable is still here. It's still seed. Okay, so now we see there are two different sets of values. One is the environment variables and the other set of shell variables. So you see the difference here, but I think this example just confuse you even more, right? You now get very confused. Okay, so what if we have a variable? So is it environment variable or is it a shell variable? Okay, so this looks very confusing. So now the next slide will explain everything. So when we run a process, this is the the parent process. When we run a process, then when we start this parent process, then the environment variables from the operating system will be copied to the another set, and we call them shell variables. So all of whatever variables in the environment variables will be copied to shell variables. So we have these two sets, looks identical, but they are in different location of memory. So we copy everything here and make them become shell variables. And when a shell runs, it only can change shell variables. It cannot change environment variables. So you see that in the previous process, when we run a program, then we have a log name here, also seed, because we have the environment variables of this process copied into the shell variables. That's why we initially that we see that log name in the shell and log name in the environment are the same. Now we change log name here. Actually only change the shell variables, not the original environment variable. So we can only change shell variables here, but we cannot change the environment variables. During the time of our run, then we can also define new variables. For example, foo and bar, and remember the previous example, then we can define new variable here, but they are only shell variables. Some of the user-defined variables here can be exported, and some are not. If we use export command to a shell variables, then we can make them inherit by a child process. If we don't export a variable, shell variable, then it is not inherit in a child process. So let's see if we have a parent process here and we run a new process, a child process. When a child process is run, at the time it is executed, then all the shell variables from the parent process is copied into and becomes environment variables for the child process. Not only the shell variables copy from the parent shell variable, the parent shell environment variable here, so but also the user-defined variables that are exported, also copied into the environment variable of the child process. So to summarize what we have in these diagrams, we have a parent process. When the parent process runs, all the environment variables are copied into the its shell variables. And when we run a new process, a child process, then these shell variables will be copied and become shell environment variables of the child process. But not only this set of the original parent's environment variables copied to the child process, also whatever user-defined variable in the shell here, if they are exported, they also be copied to be part of the environment variable of the child process. But if we define some shell variables, then we don't export them, then they stay with the parent process. They are not copied to be environment variables of the child process. Okay, so actually it should be like this. When the child process runs, then this set of environment variable will be copied into shell variable of the child process here. So whatever the child process can change, only the set of shell variables, not the environment variables. Okay, so that is how environment variables are passed from the parent process to the child process. In the previous one of the previous slides, we say that when we run a child process, then all environment variables of the child process, okay, are copied, are inherited from the parent process. So here, these all variables are copied to the child process. but also some new variable defined by the parent process can be inherited by the child process as well. So is this diagram clear? Are you clear? Or I forgot to record? I forgot to record. Let's stop for a while so I can record this. Start recording. Oh, I think, am I recording or I don't remember. Am I recording or not? Let's check. Oh, yes, I'm recording. Okay, good. So no problem, we can continue. So is everything clear in this diagram? You know how the child environment variables are copied from the parent process, and what's the difference between the environment variable of a process and the shell variables, right? Do you know the difference now? So do you see the difference now? You see the difference now. If you are unclear, you're still not very sure what the difference are, then you can ask. Okay, is everything clear? You need me to explain in more detail. Okay, you don't see the difference. Okay, then okay, I should repeat it quickly, and then we do the experiment in real, for real. Okay, so when we run a process, the environment variables are managed by the operating system. So when we run a process, then we don't have direct access to the environment variables, but the environment variables are copied to another set. Then they are called shell variables. So at the time when we run a program, then these two sets are the same, but they are located in different location of the memory. So we can when we run a process, we can only have access to the shell variables, but at the beginning they are the same. So we can change the content of some shell variables here, but we can't change the environment variables. And we can also define some new shell variables here. So when we run a new process, then the environment variable of the child process are inherited from the shell variables of the parent process, and also whatever newly shell variables are defined and exported also copied to the child's environment variables. Let's go back to this example, and you see that so this is the environment variables of the current process. So its log name is seed. But when this shell is run, then this set of environment variables are also copied to the shell variables, and they have the same name. So that's why when we echo $ log name here, so this is not a shell an environment variable, but this is a shell variable. So we have the same name, but we can only access the shell variables from the shell command. These two at the beginning have the same value, so they are both seed, because this log name shell variable is copied from the environment variables. But now if we change, we cannot change the shell the environment variables, but we can change the shell variable here. So if we change log name to Bob, that means we change the copy of the shell environment variable. We don't change the environment variable, we only change the shell variable. So we change the shell variable to Bob, then we equal log name is Bob, but this is only the shell variable Bob, log name is Bob now. The original environment variable log name is still Cedar, it's not changed. Okay, we can only make change to the set of shell variables. Now we undefine the log name variables. We have no more shell variable name log name, but the environment variables still intact. Okay, it's still unchanged. Log name is still seed. Now, to make sure that we have understood the difference between the two concepts, then let's try to find out what we have in this example. So remember, we also have a command in the shell named env here. Env, when we run it in the shell, then it prints out the environment variables. But when we are in the shell, we run this command, and this command is run in a child process. That's why when it prints out the environment variables, those environment variables are only belongs only to the child process. Okay, so when we print out by env, we have environment variables of the child process. So we see how when we run env, it's actually print out this. When we run proc command here like this, then we print out the environment variables of the parent process. Okay, so we have this is proc when we run. So here is the, let's see where this is screen. Okay, yeah, we have here proc $$ here. Okay, environment, and here we have env, and this command locates in the bin directory of the user directory there. Okay, so you see that when we run env, it's run in a child process. So when it prints out the environments, it's only the environments of the child process. But when we look at procs folder, virtual file folder here, then we see the environment variable of the current shell that we run. Okay, so now we see that we use these two different commands to see that how this set of parent shell variables are copied to the shell, the child process. Now how these are copied to the child process, we see in this example. Okay, now let's take a look at it carefully. We use string procs $$ environment here to display the environment of the current shell, of the parent shell. So we only display the log name variable only. So we see log name is Cedar, which is the current user. Okay, and now we are in the parent process, right? So this is the parent process. We define log name 2 is Alice, but we don't export this variable. And this is a shell variable. This is not an environment variable because we defined it locally in the shell here. So when we run, we can only change the shell variable. And another variable, log name 3, we assign it to Bob, but we export this variable. Okay, now we run env, that means we create a child process, and we see the environment variable of this child process. So we only display whatever variable that starts with log name then what do we see here? Do we see log name Sid? Do we see log name Alice? Do we see log name 3 Bob? So we have 3 different variables here. So how many variables or what variables do we see here if you run env in a child process? Now, this is the question I want you to answer. If you have understood the difference. Okay, now I'll say again that we have the environment variables log name seed of the parent process, but in this parent process, okay, we defined a shell variable log name 2 and another shell variable log name 3. We export log name 3 and now we run a child process. Okay, so and this child process will print out all of these environment variables that start with log name. So among these 3 variables, so which one do we see here in the child process? Okay, so which one? If you're not so sure, then take a look at this diagram. Okay, we use env to display these sets of variables, and this set of variables inherits from the parent process. Okay, the parent process, that means that whatever in the environment variables of the parent process will be copied to the child process, and also whatever defined and exported in the parent process also copied to be the environment variables of the child process. Okay, so so what do we see here among log name 2, log name 3? Which one do we see here? Does anybody know? We see Sid and Bob. Yeah, excellent. Sid and Bob. Now let's see. When we see Sid and Bob, what's the reason? Because this is an environment variable of the parent process. Okay, so environment variable of the child of the parent process, they're copied into the shell variables of the parent process, and all of this copy to be the environment variable of the child process. So if it appears in the parent environment variables, it also copy to the child. Okay, so seed log name seed here is an environment variable of the parent process, so it should be inherited by the child process as well. And among these 2 shell variables, log name 2 is not exported, while log name 3 is. So log name 3 is exported. That means it becomes like globally public available. So this one will be inherited by the child process. So that's why when we run a child process, we only see log name Sid and log name Bob. Log name 3 is Bob. Log name 2 is kept private for the parent process. It's not exported. So we'll only see these 2. So now, next, if we unset log name, that means we remove this. Okay. So when we run environment grep log name again, what do we see? I have to remind you that all these 2 things that we see here, they are all shell variables. They are not environment variables. Okay. Even we say we print out this, but actually because everything here in the environment variables of the child process will be copied into the shell process of the child. So it's only print out the copy of this. Okay. So now we unset log name. That means we try to remove this away and we try to display it again. Environment grep log name. So what do we see here? For the child process, we have these 2 inherited from the parents, right? And now we unset log name Sid and we run the child process again. So which one's still there? Which one still appears here? What do we see now? Only Bob, correct. Only Bob. So we only see Bob because this is the shell variable. It's copied from the here. Look at this. When we run, we actually have a copy of the shell variables. Here we have a set of shell variables. Here, copy from the parents. Copy from the environment variables. So what we see in the child process, what we can do with the child process is only the shell variables, not the environment variable. We can only change these shell variables. So when you see these two, when we see these two variables, they are shell variables. So when we remove one of their variables, then we only have the other variables left. So long entry is the only one left because we remove log name. So when we remove log name, we only have log name 3 left. Okay, so I hope now all of you are pretty clear about what's the difference between shell variables and environment variables. This mechanism is pretty, complicated if you're not familiar with it. So, but all you have to do is that to remember this diagram. Okay, when we start a program, then all of the environment variables are copied to the shell variables, and we can only change the shell variables. We cannot make change to the environment variables. If you want to make change to environment variables, we can only make our shell environment variable changed and then create a new process. So when a new process runs, it's copied everything that we exported here and the copy of the original shell variables here. It copied and creates the new environment variable for the child process. So whatever we change here can make change to the environment variable, but only of the child process. We cannot make change to the environment variables of our process. Okay, so I hope everything is clear until now. So if everything is clear until now, that means we are ready for making attacks, right? If we are still not so clear, then we cannot attack. Okay, so now talk about how to attack a program when it uses environment variables. So when we attack a program, we have to use the different channels that program takes input from. So we will try to manipulate the input to make them bad inputs, and in expectation that the program will create bad outputs, right? So for when the program runs, there are many different channels that it takes the environment variables. It appears when we compile a program. So when we compile a program by GCC, actually GCC use a linker. A linker is a module in GCC program that links different object files together to make a binary executable program. So if we have different modules of a program, we want to link them together to make one binary executable program, then we have to use linker. So this is one way to attack the program, because when linker runs, it has to look for libraries and different components of the program, and in order to know where are those components, then it has to take a look at the environment variables. And another attack surface is application. When we finish linking the program, then we have an application, right? So when we have an application we runs, then the application may still have some libraries dynamically linked to the program. So if the program, when at the time when it runs and is still looking for some library to run, then it is where we can exploit. And if an application, when a program here runs another program, then it's also the channel that we can exploit. And another project, when an application may run some parts of the application code. This application code takes value from environment variables, and if it takes, then we can exploit. So these are the four different attack surfaces that we gonna take a look at today. Okay, first we take a look at how we attack a program by using a linker. Now, I'm sure all of you familiar with this program. It's called Hello World. Hello World is the first written by Dennis Ritchie and Ken Thompson. They are the parents of Unix operating system and also the parent of C language. And in the first book about C, and they wrote this short program, which now becomes very famous. Whenever you learn a new programming language, and surely this will be the first program. It shows how simple that programming language is. So we have this program, we just print out a string hello world, but we will look at two different ways we compile this program. The first way is the dynamic linking, and the second way is static linking. Okay, I'm not sure if you have a concept for what dynamic linking and static linking. Does anybody know in Windows we have what we call DLL? In Windows we have DLL file.dll. So do you know about this? So DLL file, if you know about DLL file, then you have a notion of what dynamic linking is. Okay, so you don't know, you haven't learned about it. So when you learn when you take the Linux course, then do you also learn about dynamic linking? No. Okay, so if you don't know, then it's okay. I'm gonna explain it in more detail. Okay, so now let's compile our program, our simple program Hello World, in two different ways. First, the first line here, you see that we run GCC, and we should compile it normally with the option like O here, output. This is the name of the output file, the destination file, executable file, and this is the source program. Okay, so we call the output hello dynamic here, and the second line we compile with the static option, and we output this the destination file named as the hello static. What you observe when we list out the current folder, you see that hello dynamic is only 7K, while hello static is 700K. So it's 100 times bigger than hello dynamic, right? So surely when we compile a file using static option, then we occupies a lot more memory, 10 times more. And hello dynamic is very small, very light, so when it runs it doesn't occupy much memory. So what's the difference between these two? Okay, let's explain it shortly. Okay, when this is the, let's think this is the memory, and when we load a program, this is our hello world. Yeah, when we run a program here, then hello world will have a function named printf here, right? So if everything is static, so if it is static, that means the code of the printf should be parts of the executable binaries. So our program hello world has to include the binary code of the printf function as parts of this binary compilation, right? So this is the static one, and the dynamic one is that when we have hello world here, hello, so it doesn't contain the printf within its compiled code. When it call, it jumps to different parts of memory where the library libc library here, then the printf function is located here. So our program is very small because it doesn't contain the printf binary code. It should jump to somewhere else, make a call to printf, right? So the size of this program is very small. Actually, in the static version, hello doesn't only contain the binary code of the printf, but also contain the binary code of the libc library. So you see that all libc libraries, when we compile with the static option, will be included in the hello program. That's why its size is so big, it's 700K. And in the dynamic situation, when we have only 7K, because the libc, the code of libc is located somewhere else in the memory. So this is not part of our memory, not part of our binary program. When we call it dynamic linking, is because it's because this library is loaded into the system memory and it resides there. Okay, if we have other program running, for example, we have another program which make a call to printf, here another program which make a call to printf, then it just need to locate the location in the memory of printf and make a call. So you see that we have many programs, but we don't have to load libc library many times into the program. In the situation of static linking, then if we have multiple program running, then we have multiple copies of libc library here in the memory, and that is really a waste of memory, right? We have a lot of copies of the same thing, but with dynamic linking, we have the library only loaded once into the memory, and any program that wants to use its function then should make a call to the function of this library, and there is only one copy of the library. That's the reason why all operating systems today, like Microsoft Windows or Linux, Unix, use dynamic libraries rather than static library. So that's the reason why we see that hello static is much larger in size than hello dynamic here, because hello static has to include a copy of the libc library inside it. So you see the difference between dynamic and static linking. Dynamic linking has a lot of advantages. It means we can profit a lot of dynamic linking benefits. So that's why when we compile a program normally, we have the dynamic version of dynamic linking version. Nowadays we don't usually compile a program using the static linking method anymore. But we have to pay it with a price. What is the price? The price is security. Now we take a look at disk, and then we understand that where attacker can attack our system by try to profiting the dynamic linking. And remember that in Windows we have DLL file is the dynamic linking libraries. So you see in Windows there's a lot of file added with DLL, which stands for Dynamic Linking Library. Okay, now if we compile hello world dynamically, so we have this I don't see it here. Okay, so if we have hello world, the dynamic version here running, this is the dynamic version, so it doesn't its code doesn't have the printf function, right? This code doesn't have the printf function because it's compiled dynamically. So when we run, there is one pass missing. We cannot run this program yet because we don't know where the printf function locates in the memory. So when we run this program, it's not executed yet. We run this program, then the loader, the shell will use execv to load this program into the memory, and that we call the loader. When it loads our program into memory, it doesn't run immediately yet. It had to pass through a dynamic linking process. Is it here? The loader then asks the dynamic linker program in the operating system. We call it ldlinux.so here. So this is the dynamic linker, and the loader asks the dynamic linker to find where is the printf function. So the dynamic linker finds the printf function, and then it link the address of the printf function to our program. So our program now knows the address of the printf function, and now when after the dynamic linkage, then we jump to the main program to execute the code, because the code now knows where the printf function is. So when the main function here runs, then it's jump to the printf and print out. Okay, so we have to go through a dynamic linking process here. The problem is that when this dynamic linker runs, it also takes some environment variables at its input, and this is exactly where attackers can attack the dynamic linker. Dynamic linker will try to provide bad inputs to the dynamic linker in hope that they can manipulate this dynamic linker. And let's see how. Okay, to understand that what dynamic libraries are still missing in our dynamic compilation version, then we can use the command ldd here. We run ldd, and the input is our binaries code. Then if we compile a static version, then there is no dynamic library missing. So everything is complete, it's inside here. So it doesn't take any additional piece of code. Everything is in here. So it's very safe. If we run a static program, we save because it asks for no more inputs. But if we have a dynamic version of Hello World, and we try to look at how many missing libraries still needed, then we see a list of missing libraries here. linuxgate.so, after this dots is the version. We don't care. Okay, first linuxgate.so is the dynamic library to allow the system call to the kernel. And next is libc library. This is exactly where the printf function is in. Okay, so this library contains all basic inputs and output libraries of a C program. And another one is which is missing is the dynamic linker itself. So when we run a dynamic program, it first locates the dynamic linker, and the dynamic linker will try to link the libraries in libc here to our program. But there is a risk. Okay, dynamic linking gives a lot of benefits because it saves a lot of memory, and we have a lot of memory free for running more programs. But this also means that some parts of our program code is still missing. So when this piece of code is missing, then we have to look for somewhere else for the missing code. And when we look for somewhere else missing code, then attacker may replace the missing code with their own code. So when we run, we actually run their code, the attacker's code. Okay, so let's find out how. So when a dynamic linker runs a dynamic program, it relies on environment variables. The first environment variables is LD preload. Okay, dynamic link preload. Preload means in order to run a program, then we have to load some dynamic library into the memory immediately. So we have to load those libraries right immediately before we run a dynamic program. So we can specify LED preload to a dynamic library, and that dynamic library will be loaded into the memory, onto the memory before our program can run. Another environment variables relating to dynamic linking is the LD library path. So this variable contains the path to a folder where the dynamic linking program can find all dynamic libraries. But these libraries are not, we don't need them in urgent, so they can be linked to our program at a later time. So this has the most priority, and this has the lower priority. So LD in summary, LD library path points to a folder where all the dynamic library can be found. But LD preload points to a library that has to be loaded immediately before we run the program. And because there are two environment variables here, so attackers can try to change these two environment variables, and that the dynamic linker will be cheated to link another library instead of the original library. Okay, and the problem is if we run a setuid program, then actually the code that the attacker inject into our program can also run with this privilege, and that's why the attacker can take over the system. Okay, so we take another example for real. Case study number 1, that how attacker manipulates the environment variable to attack our system. Oh, but it's time to take a break. So let's wait and let's take a break. I save